Hello everyone. I'm going to give you a talk about post-quantum. Hello everyone. I'm going to give you a talk about post-quantum recursive signature aggregation for the Beam chain. So first of all, part of it is partially opinionated, so and only reflects my current personal opinion. As Dimitri explained, Poseidon-based XMSS signatures is a good candidate to replace BLS, which had very nice aggregation properties, but which unfortunately does not resist a quantum computer. The question is then how to aggregate those XMSS, so hash-based signatures, because we need this aggregation property for Ethereum consensus layer. And there are multiple ways to do it. And in this talk, we are going to focus on the snark, particularly hash-based snark, to make it plausibly post-quantum. What algorithms do we want to snarkify? Two of them actually. First, aggregate, which basically proves that you have knowledge of some signatures corresponding to ones in a bit field, and that you have sequentially verified all these signatures, and when you create a snark proof of this algorithm, you end up with a small aggregation proof. And second algorithm, merge, which basically consists in aggregating the aggregates. So you can re-aggregate already aggregated signatures. But doing this, we'll have to verify a snark inside a snark, because you need to verify the first snark proof of the aggregate algorithm, which is recursion. The question is then how to design an efficient yet simple snark. First possibility would be to have a handwritten circuit, but doing this for, in particular, the merge algorithm is a nightmare and impossible. So probably more something like a minimal ZKVM. You can think of something like Kero, but optimized for our use case, which is aggregating signature, and which actually could consist in verifying a lot of hashes. Which PCS to use? Probably WIR. First, because WIR has shorter proofs than Fry, and we want to target short proofs around 128 kilobytes. And additional advantage of WIR is that it's a multilinear polynomial commitment scheme, which is useful because you can, in a Fry-based stack, you have to commit to each column as a separate univariate polynomial. Using a multilinear PCS, you can commit to the whole Airtable as a single polynomial, multilinear, and this will additionally help to reduce the proof size. Which arithmetization to use? Probably AIR, so algebraic intermediate representation, because these transition constraints are very natural to represent the execution of an opcode. Which field to use? Probably again a small field, because this will lead to fewer rounds in Poseidon, and because we would use WIR, a multilinear PCS, we would not use the classical univariate quotienting in stars, and we can replace this with a soundcheck-based PIOP, and with the help of the univariate skip from Angus Green, we can totally remove the embedding that you previously had using small field in the soundcheck, that you had like an overhead that appears after the first round, and you can totally remove this overhead using the univariate skip. And which field in particular? Probably koala bear, because the cube map is an automorphism of the multiplicative group, and this means that Poseidon is more efficient and particularly easier to prove. The only drawback of koala bear is that it has a low two-adicity, meaning that you can only commit to less data, so you have You cannot prove a snark on a big statement, but if you use an extension degree which is a power of 2, you can increase this to adicity. And for instance, if we use a degree 8 extension field, we gain to adicity up to 2 to the power 27, which is enough to prove a validity of 2 million Poseidon permutations. An additional advantage of degree 8 for extension field would be the security level, because with a degree 4, it's impossible, even though you have a field of the size of the order of 128 bits, it's impossible to get this level of security, 128 bits. You only get approximately 100 bits of security, even with the capacity, the conjecture to capacity for the paper proximity gaps in return-one code. Actually, you could use the star conjecture, but not something you want to enshrine in Ethereum, probably. In terms of ISA, probably not RISC-V. We don't need all this OP code to only prove Poseidons. Something much simpler, probably closer to K-row. So being able to add, multiply, and to manipulate memory. Very few registers. For instance, K-row only has 3 registers, PC, AP, and FP. And there is a debate around the memory. There are 2 types of memory, read-only and read-write memory. Read-write makes it easier to write a program, but is more expensive to prove. So personally, I would argue, I'm not 100% sure, but I think read-only would offer better performance. We would also need precompiles for our computationally intensive tasks. Of course, a Poseidon precompile, but we would potentially also need precompiles to do the operations in the extension field, because in the merge algorithm, we need to verify a snark inside a snark, and verifying a snark happens in the extension field for soundness reason. And so that's why we would have in this part a lot of extension field operation, and that's why it's potentially useful to have precompiles for the extension field ADML. Here is a sketch of a potential architecture, nothing fancy, main table for the execution, tables for precompiles and memory with memory buses, aka lookups to communicate information. And to conclude, I wanted to highlight a paper by Lev, which is an indexed lookup argument. What is an indexed lookup argument? Basically, you have a column containing data, and you have another column containing indexes, and you want to prove that this third column corresponds to the correct indexes. So for instance, 1 here, it corresponds. But in previous lookups, for instance, lookup GKR, you have to commit to these 3 columns, and then you prove that the lookup is correct. But with this recent paper, you can avoid to commit to this column and only commit to a column of this size T, which is particularly useful when the column T is much smaller than the column of the indexes, which is the case for the bytecode, because each opcode will be read accessed multiple times because of the loops. So for instance, if this column represents the bytecode, the columns of the program counter and the opcode will be much longer than the bytecode itself. So avoiding to commit to this one may be interesting for us. Additionally, in K-row, you have to commit to numerous Boolean columns that represent the logical bits of the opcode, and so you would avoid to commit to lots of columns using this indexed lookup argument. That's it for me, and here is a link to some implementations related to this topic. Happy to take questions again. Thank you.
You say you're like exploring like a custom ISA, like do you think it would be something like Rita is doing, or like a different?
Rita?
Yeah.
I think something much simpler, probably. I think we need to take inspiration from Cairo. Cairo is very, very simple to understand and to prove.
Follow-up question, like if you're doing something custom, like what are your projected like timelines of like production?
We already have this part. We already have a PCS implemented with the Plonky 3 fields. We have PCS, Thomas is in this room. We have P3, we have P3, sorry. And we already have multilinear PIOP that's able to prove validity of Poseidons. We can currently do more than 100. Actually, we could do, I know how we could almost reach 200 Poseidon on a CPU and above 1 million with a GPU. The thing that remains to be done is this part with the execution table and the memory and the lookups. So we have this next field.
I have a very new question about Poseidon, but when you talk about Koala Bear, does it mean that Poseidon is over Koala Bear?
Yes.
So does it mean that in some sense it would mean enshrining a specific Poseidon? Because if someone uses Baby Bear or Mersenne Prime, they would need to emulate Koala Bear and then it would slow down all the other provers?
Yeah, you would, in this system we would have Poseidon over Koala Bear and the proof system over Koala Bear. Everything over Koala Bear.
So everything, yeah, okay. So it's in some sense it's which makes sense. It's okay. It gives advantage to one specific prime.
Exactly. We would have to choose.
Okay.
For instance, in Baby Bear, this map, which is an automorphism, Baby Bear, is to the power 7. So it's much more expensive than Koala Bear.
Okay. X5 to X5.
Yeah.
How about Mersenne Prime? Did you check? Or other primes? I don't know.
I think,
Like
I don't know for Mersenne, but I think if we could avoid the conceptual complexity of circle stars, would be great, I guess. If you can get enough performance with classical stars.
And how about Venus? Did you talk to your people?
I think some people have talked.
So this is shared confidentially, but the irreducible people have pivoted just a few days ago, and they are no longer going to be pushing Venus as hard.